In this lecture, we'll understand all of these terms in detail and why they are so important with respect to data analysis. In the previous lecture, we have discussed about visualizations. We talked about different types of charts we can create over our data, right? In this lecture, we'll understand the application of few of them to see what kind of problems we can solve. But before that, let's set the agenda for today. So we'll start out by understanding what skewness is. Then we'll talk about different types of skewness, that is left skewed data and right skewed data. We'll also see the effect of skewness over the central tendencies, that is mean median mode. Then we'll talk about outliers and different ways of detecting outliers, that is box plot and z-score. Finally, we'll talk about covariance and correlation, which helps us to understand the relationship across our continuous variables, and we'll see how we can calculate these two quantities. So without further delay, let's dive into the lecture. Now let's first understand what skewness is. Skewness is the deviation from symmetry observed in data. Skewness represents the measure of asymmetry in our data. Now let's first see what symmetrical data would look like. Now below we have given three different distribution. Let's say these are three different mountains. So this one is mountain 1, this is mountain 2, and this one is mountain 3. Now if you look at the distribution of mountain 2, let's say I dropped a line from the top or the tip of this mountain like this. What can we see here? We can see that the left side of this mountain is identical to that of the right side of this mountain, right? Which means this area or this distribution on the left side is identical to that of the right side. This is what a symmetrical data would look like. This data is symmetrical because the distribution, when divided based on the middle value or middle line, is common on the left side and the right side. The distribution is same on both the sides, right? Which means our data follows no skewness. The data is not skewed or biased towards the right or the left side. Now let's see the mountain 2. Let's say I drop the line from the top of this mountain as well. Now if I check the left side and the right side of this mountain, what can I see? I can see that left side is comparatively smaller than of the right side, right? The distribution or the dispersion on the left side is very small compared to that of right side. So this will give me a right skewed or a positive skewed data. This type of distribution is called positive skewed because the tail of the data, which is the longer side of the data, is on the right side. Similarly, if I drop a line for this distribution and compare the distribution on the right side to that of the left side, I can see that the distribution on the right side is very small compared to the left side. And the tail of my distribution is on the left side. Hence, this will be left skewed or negatively skewed data, right? So a symmetrical data is something which is neither right skewed or left skewed. And if we divide the distribution into two equal parts based on the middle value, we'll get the identical distributions on both sides. For right skewed data, the tail of the data or the longer distribution of the data will be on the right side. And for left skewed data, the larger distribution will be on the left side, right? Let's understand this further with an example. So let's say this is the data I have. My data is 1, 2, 2, 3, 3, 3, 4, 4, and 5. Let's first see how it will look like if we plot this data. So on the x-axis, I want the numbers or the observations in my data. I only have 5 different observations, which is 1, 2, 3, 4, and 5, right? 1, 2, 3, 4, and 5. Okay. And on the y-axis, I'll show the frequency of these observations. Now let's count how many times 1 occurred in our data. It only occurred once. We'll plot 1 here. Let's just label the y-axis as well. This is 1. This is 2. This will be 3. Now we plotted 1. Now let's plot 2. It is present in our data twice. So the point will be around here. 3 is repeated 3 times, so the point will be here. 4 is repeated 2 times, the point will be here, and 5 repeated once, so here. Let's connect all these dots. So after connecting all these dots, this is what my distribution is looking like for this particular data set. Now, let's do the same thing we have done with the previous example. Let's drop a line from the top of this data set. I can see that this side, which is the left side, is identical to that of the right side, right? This distribution, which is from 1 to 3, and this distribution from 3 to 5, both have the distribution of 2, right? So this represents a symmetrical data because when divided into two equal parts based on the middle value, so which type of central tendency should I use to get the middle value in my data? I would use the median of my data, right? Which is the central observation. So for this particular data set, we can see that 3 is on the middle where 4 values are below 3 and 4 values are after 3 as well. And this represents my median value. So 3, which also represents my median, divides my data into two equal parts, right? So this data distribution is symmetrical, and we can validate it as well. We can validate this by proving this. So in a symmetrical data distribution, the mean, median, and mode all will be same. Basically, all the central tendencies will refer to a same value. Now let's calculate the mean for this particular data set. Mean will be sum of all these terms, which will give us 27 divided by total number of observations, which is 9. So we got 3, right? Middle value for this data set, which is the median, is also 3. We have already seen that 3 is in the middle, right? And the most frequent element, we can see that 3 has repeated 3 times, right? The most frequent element, which is mode, is also 3. We can see that all the central tendencies have same value, hence the distribution is symmetrical. Now let's look at the right skewed distribution. So let's say I have this data. It's the same as the last data, just this value is replaced from 5 to 50. Now let's see what kind of distribution this data will follow. Let's just quickly plot the points. This will be 1, 2, 3, 4, 5, and somewhere far along will be 50, right? Let's just extend this line. Extend this line like this. Somewhere around here we have 50, right? Now, if I plot the frequency of these points, let's just quickly plot them as well. 1 is repeated once, so it will be 1. Here it's 1, 2, 3. So 1 is repeated once, I got 1 here. 2 is repeated twice, so here. 3 is repeated 3 times. 4 is repeated twice. And 50 is repeated once. Now let's connect these dots. Now this is what my distribution is looking like. If I drop a line from this particular mountain top, I can see that the distribution on the right side is far more than of the left side, right? This is the left side, this is the right side. The distribution on the right side is comparatively very high. So this will follow a right skewed distribution, right? This will follow a right skewed distribution because the tail of this distribution is on the right side. Now let's see how this affects our mean, median, and mode. So mean, which is mu, for this data set will be sum of all these terms, which will give us 72 divided by total number of observations, which is 9. So we got 8, right? So mean for this data set is 8. Median, which is the middle value, is again 3, because 3 is in the center. There are 4 values in the right side of the 3. There are 4 values in the left side. So median will be 3, and mode will again be 3 because 3 is the most frequent element, right? So here I can see that my mean is affected because of this particular value. If I plot the mean in my data set in the distribution, it will come somewhere around here after 7. Here my mean will lie, right? Now the problem is central tendencies refers to the middle or central elements in our data, but we can see the mean is towards the right side of the data distribution, right? This data distribution and this data distribution, we can see mean is on the right side because of this particular outlier where a very high value is affecting the mean. We can say that mean is prone to outliers, where outliers are nothing but an abnormal observations or something that is not following the general trend of our data or general distribution of our data. We can see most of our values are around 3 and 4, but there is a value 50 which is very high compared to other values, right? We'll discuss outliers in detail further in the session. For now, let's have a look at the left skewed data as well. So in this data again, we can plot the points. This is the data given to us. We can plot the points like this. Let's say this distribution will go like this. We have -8, -1, so on till -8. Here we have 1, 2, 3, 4, and 5. Right? Let's plot the frequency of these points. So 1, 2, and 3. So -8 is repeated once, it will come here. 2 is repeated twice, it will come here. 3 is repeated 3 times, it will come here. 4 is repeated twice, and 5 is repeated once. So let's connect these dots as well. It will look something like this. Now if I look at my distribution, and let's say I dropped a line from the top, which looks like this, I can see that the tail of my data distribution is on the left side. So this will be left skewed data. Now let's see how it affects our mean value. So mean for this data will be sum of all these terms, which will be 18 divided by total number of observations, which is 9. So we got 2. Median for this data again will be 3 because there are 4 values on the right, 4 values on the left. Median is 3. Mode is again 3 because we have 3 repeating 3 times. Now we can see that the mean of this data set is falling here, right? This represents our mean value. So what happened with right skewed data? Our mean shifted towards the right of the central value, right? But in this case, it shifted towards the left of the central value. So what we can do is we can deduce this much from this information, that if our data is positively skewed or right skewed, the mean will be towards the right, median will be in the middle, and mode will be the most frequent element, which will be somewhere around here, right? We can say that mean is greater than median, which is also greater than mode in case of right skewed data. And in case of left skewed data, it will be reversed. Median will still be in the middle, mode is shifted towards the right side, and mean is shifted towards the left side of the median. So here, mean is smaller than median, which is smaller than mode, because most frequent element will be somewhere around here, right? Most frequent element will be somewhere around here, where the top of our distribution is there, tip of our distribution, which is the most frequent element. Now, so far, we have discussed about the skewness in our data, where symmetrical data would not have any type of skewness. A positive skewed or right skewed data will have a larger distribution on the right side, and left skewed data will have larger distribution on the left side. Then we have seen how the skewness of data affects our central tendencies. So in case of right skewed data, mean will be higher compared to median and mode. And in case of left skewed data, mean will be smaller than median, and median will be smaller than mode, right? Now let's discuss outliers. Now outliers are data points which is away from the general pattern. As we saw, as we already saw, outliers are something which causes the disruption or which causes the asymmetry in our data distribution, right? Outlier is the odd one out in our data. So let's see the effect of outlier on mean and median. So let's start with mean. If we calculate the mean of this data set, which is sum of all these observations divided by the total number of observations, it will give us 26. Let's say I replace this last observation. Instead of 33, I'm having 73 now. Now let's see what will be the mean of this particular data set. The mean of this data set will be 30. Now if you see, with just change in one of the observation, our mean is shifted towards the right side. And if I want to see where the mean will lie in the first data set, D1, the mean will be somewhere around here, right? Mean is 26, which actually is in the middle of the data set. But if I check for the second data set, my mean is 30 and it will be somewhere here, which is not in the center because I can see the distribution on the left side is higher compared to on the right side, right? The total number of observations on the left side is higher compared to the right side. This is how outlier can affect our mean value of the data. But if we calculate the median for these data sets, in both the cases, it will pick out these two central elements and average of these two will be our median, which will be 26 in both the cases. Hence, when our data is affected by outliers, it is suggested to go with median rather than mean because our mean will be affected. Now, let's discuss outlier detection. Let's understand what outlier detection is. Outlier detection is the process of detecting the data points which are not as per the general pattern in data. Or, in other words, outlier detection is finding out the outliers in our data. So we'll discuss two ways to find outliers in our data in this session. One is using a box plot and another one is z-score. Let's discuss each one of them in detail. So let's first see a box plot. So if you remember, in the visualizations module, we discussed box plot where this box represents our quartiles, Q1 and Q2, and this line represents our median, right? This and this line represents our whiskers, which is this one is lower whisker and this one is upper whisker, right? And the value of whiskers or the minimum value according to the interquartile range, which is nothing but the length from here to here, which is Q3 minus Q1, is calculated as Q1 minus 1.5 into IQR, right? Q1 minus 1.5 into interquartile range, right? And this maximum value is calculated as Q3 plus 1.5 into IQR. Now, the outliers are some values which do not fall within this entire range, right? If something doesn't fall in this entire range, even with the maximum and minimum value according to our IQR, we can say that those points are outliers which do not follow the trend of our data or the general distribution of our data. So these points outside the upper and the lower whisker of the box plot are outliers. This is how we can visually identify outliers in our data. Now, let's discuss z-score. Z-score tells how many standard deviations away a data point is from the mean standard score. Z-score tells how many standard deviation away a data point is from the mean standard score, right? And z-score is calculated. Z-score is calculated for a given value or for a given observation. X will reduce the mean value, which is mu, and divide it by the standard deviation of our data. So for example, if the mean value of data set is 30 and we are checking the observation where the value is 45, and let's say the standard deviation for this data is 5, we can do 45 minus 30 upon 5, which will give us 3, and it represents that a certain variable 45 is 3 standard deviations away from the mean value. Okay, now let's understand what standard deviation actually represents here. Let's say this is my data distribution. Let's say our data is symmetrical and this is our middle value or the mean. Mu is in the middle, right? So first standard deviation means going away from mean on the right side and on the left side, where these 2 points x and y is calculated as x is equal to mu, which is mean, minus standard deviation. So if we go towards the right side for a measure of standard deviation, we'll get the first standard deviation on the left side. Okay. Similarly, we can go on the right side as well by adding the standard deviation, which will be mu plus standard deviation. This will give me this range. Just give a different color. This range. Okay, this is on the right side. So first standard deviation means all the values which fall within this range are considered to be falling in the first standard deviation, right? Similarly, I can find the second standard deviation by going more towards the left side and the right side. So this will be x dash. Let's say the second standard deviation will be mu minus 2 into standard deviation, because we are moving 2 standard deviations away from mean on the left side. And on the right side as well, we can do mu plus 2 standard deviation, which means we are moving 2 standard deviations away from the mean on the right side. Generally, so in most of the data distributions, 3 standard deviation will cover around 99% of our data. So 99% of our data will fall within 3 standard deviations. 2 standard deviations will cover roughly around 95% of our data, and first standard deviation will roughly cover around 65 to 68% of our data. Okay. Now let's jump back to z-score. So z-score helps us to identify a certain observation. For a certain observation, how much standard deviation away we should move from the mean to get that observation. Let's see it with an example. So in our data, we have numbers from 20, 22, 25, 26, and 28. And there is one very high number, high value compared to other numbers in our data, which is 59. This is our outlier. Now let's see how we can identify this outlier using z-score. So we'll list down all the observations. Then we'll subtract the mean value from this observation. Some mean for this data set is 30, and we'll subtract 30 from each observation. We get 20 minus 30 as minus 10, 22 minus 30 minus 8, 25 minus 30 minus 5, and so on. 59 minus 30 will give us 29, right? Then we'll square all these differences. We squared all these differences, which will give us minus 10 square 100, minus 8 square 64, minus 5 square 25, minus 4 square 16, minus 2 square 4, and 29 square 841, right? The average of all these squared distances will be my sigma square, which is variance, right? Now using this variance, I can just do the under root of variance will give me standard deviation, right? And standard deviation for this set is 13. Now I'll calculate the z-score for each and every observation in my data. So z-score is x minus mean upon standard deviation. So here my x is 20, 20 minus mean value, which is 30, which will give me minus 10, minus 10 upon 13 will give me minus 0.76. Similarly, we can find the z-score for each observation, and we can identify that all of these observations fall within first standard deviation of our data distribution. Why? Because none of these values cross 1, either on the negative side or on the positive side, right? But we can see that this particular value is 2.23 standard deviation away from the mean value of our data, which depicts that this is an outlier which is falling in the third standard deviation of our data, while all the other elements are falling within first standard deviation. This falls in the third standard deviation because this value is above 2, right? This is how we can identify outliers using z-score. Now, before we move forward, let's have a recap of what we have covered so far. We have talked about outliers, which are data points which do not follow the general pattern of our data, right? These are like the odd one out in our data. Then we saw the effect of outliers on mean and median, right? So median is not actually affected by outliers because it will represent the central value in our data. But if we talk about mean, we saw that if there is a very high value in our data set, then our mean will shift towards the right side. And if there is a very small value, then our mean will shift towards the left side. Then we talked about different techniques of detecting outliers in our data. We talked about box plot and z-score, where box plot helps us to represent the distribution of our data, right? And the values or the data points which do not follow within the range of lower and upper whisker of our box plot are considered to be outliers. Then we talked about z-score, which helps us to identify how many standard deviation away should I move to get a certain observation in my data, right? So we can calculate the z-score for all the observations in our data, and using that information, we'll understand if there is a observation where we need to move a lot of standard deviation away from the mean value to get that particular observation. That value is considered to be outlier. Here in this example, we can see all the values in our observations fall within the first standard deviation, but there is one value which fall in the third one. So that is considered to be outlier. Now let's talk about covariance. Covariance is a measure of linear association between two features in our dataset. So what it does is it helps us to find a proportionality within our features. So here feature represents numeric features. And what covariance does is it helps us to identify how the change in one of the feature affects other features, right? So let's first break down the formula for covariance, then we'll discuss covariance with an example. Covariance between feature X and Y, these are the two features we have, is calculated by taking the average. Since we are doing sum here and we're dividing it by number of observations, we are taking the average of, now what does this represent? Xi minus X bar. This represents the difference of a certain observation, difference of ith observation with respect to the mean value, right? With respect to mean value of X. Similarly, this represents the difference of ith observation with respect to mean value of Y. So we are taking the product of these differences, right? And we are doing the average of those products. So what we are doing is average of multiplied differences with respect to mean for feature X and Y, right? This is what our covariance represents. It is the average of multiplied differences with respect to the mean value for both the features. Now let's see one example. So let's say I want to identify the covariance between two sets where one of my sets represents the hours of study for a student. That is this. So we have 5 observations and these represents the number of hours. So this is 1 hour, 2 hour, 3 hour, 4 hour and 5 hours. And we want to identify the relationship of these hours of study with respect to the marks student is scoring in the exam. So we have marks of students. Those are, let's say, 20, 40, 60, 80, and 100. Right? So I want to identify how the amount of hours that a certain student is giving towards their study affects their scores in the exams or their marks in the exams. So for that, we can use covariance, right? We can use covariance. Let's consider this one as X and this as Y. So we want to get the covariance of X and Y. And the formula for calculating covariance is summation of Xi minus X bar, right? Yi minus Y bar and whole divided by n, right? This is our formula for covariance. Let's calculate all these values. Let's list down our X and Y. We will require Xi minus X bar. We'll require Yi minus Y bar, right? and we need the multiplication of these two. So xi minus x bar, yi minus y bar. Now let's quickly calculate all these values. So 1, 2, 3, 4, 5. These are the values I have for x. 1, sorry, 20, 40, 60, 80, and 100. These are the values we have for y. Now let's calculate xi minus x bar. So we'll require the mean value, right, to calculate this. So let's calculate the mean values for both the data sets. What will be our x bar? X bar will be sum of all these numbers, which are 1 plus 2 plus 3 plus 4 plus 5, which will give us 15 divided by 5. We have 5 observations, right? So we'll get 3. Similarly, we can find y bar as well. So y bar will be sum of all these, which will give us 300 divided by 5, which will be 60, right? So we got the mean value for both the data sets. Now let's calculate xi minus x bar. So 20, sorry. Now let's calculate xi minus x bar. So 1 minus 3 will give me minus 2, right? 2 minus 3 will give me minus 1. 3 minus 3 will be 0. 4 minus 3 will be 1. 5 minus 3 will be 2. Similarly, we can calculate yi minus y bar as well. So 20 minus 60 will be minus 40. This will be minus 20. This will be 0. This will be 20. And this will be 40. Now we need to multiply these values, right? So we got 80 here, 40 minus 40 into 2, right? So minus will be cancelled out. We'll get 80. Here, if we multiply these two, we'll get 20. This will be 0. This will be 20. And this will be again 80. Now what we want to do is we want to take the average of all of these. So average of all these numbers will be our covariance. So covariance of x and y will be 80 plus 20 plus 0 plus 20 plus 80 divided by n, which is number of observations. We have 5 observations. So this will be 100, 200 by 5, which will give us 40. So the covariance between these two is 40. Now, what does this value actually represent? What does this value actually represents? Since we got a positive value here, we got positive covariance, right? We got positive covariance, which means that the two features have a positive relationship. Positive relationship. Since 40 is greater than 0, we can say that they have positive relationship. Now there would be a case two features can have negative covariances as well. So in case of negative covariance, we can say that there is a negative relationship between the features. So negative covariance represents negative relationships, which means if I change or if the values in one feature varies, then it will have a negative impact on the other feature, which means if there is an increase in the first feature, there will be a decrease in the second feature. In case of positive relationship, we can say that if there is an increase in the first feature, there will be an increase in the second feature as well, which we can observe with this data as well, right? We can see with increase in the number of hours students are giving for studies, we can see their marks are also going up, right? For 1 hour, we are getting 20 marks. For 2 hours, we are getting 40. And for 5 hours of study, we are getting 100 marks, right? So this is how covariance helps us how the change in one feature affects the other. Now let's see how covariance can be useful in a real life scenario where we have the data set. Here I have the data set of automobiles, right? We have features like the body style, fuel type, horsepower, price, combined mileage. So this represents the average of city mileage and highway mileage. We have curve weight and engine size, right? We have two categorical features in this data set, and there are 5 numeric features. Let's say I want to understand the relationship between these features, right? I want to understand how the change in one of the feature, how the change in horsepower affects the price of the automobiles, or how the change in horsepower affects the mileage of the automobiles. So we can check that by checking the covariance between our features. So these are all the 5 numeric features we had in our data, right? And this here represents the covariance matrix. This represents the covariance matrix. Now let's understand how we can read this matrix. So if you see, we have all the five numeric features on all the five numeric features as the rows and the columns as well, right? So what this depicts is, for each of these row and column, let's say I'm talking about engine size and curve weight. So we got this value, right? This value represents the covariance between engine size and curve weight. This represents the covariance between engine size and curve weight. And we can see that this is a positive value. This is a positive value. So we can say that with increase in the engine size, the weight of the automobile is also getting increased. Similarly, let's identify the relationship between combined mileage and horsepower. So we'll refer this value, horsepower and combined mileage, right? Now here we can see we got a negative value. We got a negative value for covariance, negative value for covariance between combined mileage and horsepower. So what does this mean? There is a negative relationship between these two features in our data, which means if we increase the horsepower of our automobile, the mileage is getting reduced. That makes sense, right? If we purchase a car with higher power, they would have low mileage, right? Now let's see one more relationship. Let's see a relationship between price and the weight of the car. So here also we got a positive value, which means there is a positive relationship here. Positive relationship. And why is it so? Because because heavier cars heavier cars will have a better engine as well, right? A better engine will have good horsepower as well, right? They will have good horsepower as well. And hence, since we are getting an expensive engine, the price will also go up. Hence, there is a positive relationship here. Now, let's talk about one more technique of getting the relationships between our features, that is correlation. Now, correlation mostly works the same way as the covariance, but it gives us much more insights towards the actual relationship between the features. So, correlation is the standardized measure of strength and direction of the linear relationship between two variables. It is the standardized measure of strength and direction of the linear relationship between two variables. So, if we check covariances of different features in our dataset, we can see that we got many random values, right? These are not generic values. So, to make sense out of them, how is 2 different than 6? We are not getting that understanding here, right? We know that 6 is greater, right? But how exactly the change is different between these two? Both of these has a positive change, but how much does the change affect? So for that, we'll use correlations. Correlation is always going to be within the range of -1 to +1, where -1 represents negative relationship and +1 represents positive relationship, right? +1 represents positive relationship. Now these are extreme values. These are minimum and maximum values. So in general cases, our correlations may not be equal to 1 or -1. They will be somewhere within this range, right? Somewhere within this range. We also have a value 0. 0 means no relationship. No relationship. So how we can understand correlations is, if we have this line, in the middle we have 0. If we have this line, let's say in the middle we have 0, here we have 1, and here we have -1. So if the value of our correlations for two features fall within this particular range from 0 to 1, we can say that they have a positive relationship. Positive relationship. And if the value of correlation between two features fall within this range from -1 to 0, they will have a negative relationship. And the higher these values will be, either on the positive side or the negative side will depict how much is our correlation or how much the change in one variable actually affects the other variable. So as we've discussed that covariance correlation between x and y is equal to +1, then we can say they are having very high correlation, very high positive correlation. And if it is -1, we can say they are having very high negative correlation. So the formula of calculating correlations is covariance between the two features divided by sigma x into sigma y. Now what does sigma represent here? Sigma, we know that it represents standard deviation. Standard deviation, right? So correlation between two features x and y is calculated by calculating the covariance and will divide it by the multiplication of their standard deviation. So what we can do is, for the same example of hours and marks, we saw that the covariance is 40. Now let's say I want to find the correlation between these two features, right? So what I can do is I can just calculate the standard deviation. I can calculate the standard deviation. For that, I'll require these and I need to square them to get the variance. So xi, let's have it in a different page. Our x is this, y is this. X minus x bar square will require y minus y bar square as well. And we need sigma square x, sigma square of y. Let's calculate these. For x is 1, 2, 3, 4, 5. This is 20, 40, 60, 80, and 100. Let's calculate these values as well. We have already done xi minus x bar. So these are -2, -1, 0, 1, and 2. So -2 square will give us 4. -1 square, it will be 1. This will be 0. Again, 1 square will be 1. And what is the last value? 2 square, it will be 4 again. Similarly, let's calculate these as well. So 40 square, 40 square will be 1600, right? Negative values are cancelled out. 20 square, this will be 400. This is 0. And we have 20 and 40. These are going to be same, 400 and 1600. Right? Now, let's calculate the variance of x and y. So the variance of x will be average of these. So 4 plus 1 plus 0 plus 1 plus 4 divided by 5, which is going to be 5 plus 5, 10, 10 by 5, which will give us 2. So our variance is 2 for feature x. For feature y, it is going to be sum of all these, which will be 3200 plus 1. So 4000 divided by 5, which will be 800. And we know that the sigma x will be under root 2 and sigma y is going to be under root of 800. So our correlation between feature x and y is going to be 40, which is our covariance, right? 40 divided by under root 2 into under root 800. So the correlation between x and y can be found out by dividing 40 with the standard deviation of x multiplied by standard deviation of y. So what we can do is we can club these two under roots, right? We can do this, right? Which will give us 40 divided by under root of 1600, right? And this will be 40 divided by 40, which will give us 1. So for these two features, for these two features, we identified that there is a positive relationship. There is a positive relationship, positive relation with correlation of 1, which means these two are highly correlated. And the change in one of them will have a positive impact on the other. Now let's also talk about correlations across our data set. Again, we are picking the same data set of automobiles. We have 5 numeric features and we can identify the correlations like this. So this matrix here represents our correlation matrix. And similar to covariance, we can read this matrix like this. So if I want to identify relationship between engine size and curve weight, I can just refer to this value. This is positive 0.85, which means these two are positively correlated, right? And if we refer to the curve weight and the mileage, we got this value, which represents negative 0.78, which means these two are negatively correlated, right? These two are negatively correlated. And if we talk about relationship between horsepower and price and horsepower will refer to this particular value. We can see that there is a positive relationship here as well with a factor of 0.81. Positive relationship. This is how we can identify the correlations in our numeric features for our data set, right? This is how we can identify positive relationships and negative relationships across our numeric features. Now, when we are actually working on the real life data, our correlation metric will look something like this. Now, this and this represent the same information, but if we look at this particular graph, this is much more readable, right? We can see that the positive relationships are shown with the light colors, as we can see here. Positive relationship of 1 is shown with a light color. Here also we can see 0.85 as a light color, and negative relationship are shown with a dark color. So this is how our correlation matrix will actually look like when we plot using visualization libraries in Python. That will be all for our session on skewness, outliers, and correlation. Let's talk about the key takeaways of this session. So first, we talked about skewness. Skewness represents the symmetry of our data, right? Then we talked about different types of skewness, that is left skewed data and right skewed data. Then we moved on to outliers. We talked about what outliers represent. These are abnormal observations in our data. We talked about different ways of identifying outliers, that is using box plot and z-score. Then we talked about covariance and correlation, which helps us to understand the relationship across our continuous variables. Now in the next lecture, we'll be starting a new topic, that is essential Python libraries. And the first library that we are going to cover is NumPy. Till then, keep on practicing and we'll see you in the next video. Thank you for joining this session. Please do provide the feedback for this session. That will definitely help us to improve the quality of our lectures. All the best for your preparation. Happy learning.